Today we will be doing an experiment that demonstrates low Reynolds number laminar flow. Laminar flow is when fluid flows in parallel layers due to its highly viscous nature. A viscous fluid is a sticky, slow-moving fluid such as syrup, honey, or molasses. The materials we will be using in today's experiment are hand soap, a cup to put the soap or water in, water, toothpicks, a second cup to put inside the first cup, food dye, as well as a mixture of food dye, water, and soap to demonstrate the flow. For our experiment, we will be adding food dye to two types of fluids, viscous and non-viscous. The viscous fluid that we will be using is clear hand soap, and the non-viscous fluid used will be water. To begin, we will conduct our experiment in our non-viscous fluid, which was water. We poured the water into the first cup, and then placed the second cup in as a tool to mix. We then added yellow and blue food dye to the water. Already you can see the food dye begin to mix into the water. We mixed the water and food dye by turning the inner cup to the left. Once the dye was mixed in, we then turned the inner glass in the opposite direction to try and reverse the mixing. As you can see, once the food dye was evenly mixed in the water, there was no way to unmix it and bring the fluid back to its original state prior to mixing. For the second part of this experiment, we will be using the viscous fluid, which was hand soap. We poured the soap into the first cup and placed the second cup within the same way we did for the first experiment. This time, the two glasses were held in place with binder clips to prevent any horizontal or vertical mixing. Doing this will ensure that we only see concentric mixing. After some trial and error, we finally figured out a design that held the cup in place but also allowed us to turn it. We also decided to put a mat underneath of the cup to make sure we didn't spill any of the food dye on the table. We then added a mixture of food dye, soap, and water using toothpicks, just like we did for the water. We began twisting the cup to the left, and as you can see, the dye appears to be mixing into the soap. But watch what happens when we turn the inner glass the opposite direction. The food dye appears to unmix. I promise this is no trick or special movie editing. The reason this occurs is because the dye and soap aren't actually mixing. The food dye stays in their original layers and align in spiral-like shapes. These spirals do not actually intersect, so no mixing occurs, even as they are spread out over their individual layers. When the glass is turned in the opposite direction, the process is inverted, which allows the dye to return to its original position. Using the two types of fluid allowed you to see the difference in characteristics of the different types of fluid. When we mixed the food dye and water by turning the cup to the right, we were unable to return the fluid to its original state prior to mixing by turning the cup in the opposite direction. Due to the highly viscous nature of the soap, we were able to assume laminar flow, and that is why we were able to untwist the fluid and bring it back to its original unmixed state. Laminar flow has some pretty important applications. Laminar flow is used to help design and test airplanes. Chemical engineers can use laminar flow and a laminar flow reactor to study chemical reactions and process mechanisms. Lastly, laminar airflow can be used to separate volumes of air. This method can be used to separate airborne contaminants from entering an area where they could be inhaled and hurt people. Laminar flow is important to advancements in science, as well as keeping us safe and healthy.